Good day to Dr. Liu Jie. Now I would like to present my project about the queuing theory MG1 model. Firstly, we have learned some queuing system MM1 and MMK. Besides, a series of basic queuing identities that are useful in analyzing queuing models have been derived. Different cases of the queuing system have also been studied so that the model will be closer to real-life situation. However, in our real lives, the arrival and service distribution might not be as ideal as an exponential. Thus, in this project, we wish to find some identities such as the average amount of time a customer spends in the system and the average number of customers in the system with a general service time distribution G. And foremost, we'll introduce work and another cost identity. Let's define the work in the system and any time T to be the sum of the remaining service time of all customers in the system at time T. V to be average work in the system, S to be the service time, and WQ star to be the time a given customer spends waiting in queue. Next, we consider the cost rule. Each customer pays at the rate of Y per unit time when his remaining service time is Y, whether he is in queue or in service. Thus, by fundamental cost equation, the rate at which the system earns is just the work in the system. Then, since the customer pays at the constant rate of S per unit time while he waits in queue and at the rate of S minus X after spending an amount of time X in service, we have the next equation, which implies the last equation. Moreover, let's define VQ to be average work in queue and VS to be average work in the service. Note that V equal to VQ plus VS by the work we define, and we can find out VQ easily as shown by the slide. Thus, VS is just V minus VQ. The result is also shown in the slide. Now, we come to our main content, which is a system MG1. These models assume Poisson arrivals and Poisson arrival and red lambda, a general service distribution, and a single server. In addition, we will suppose that customers are served in the order of their arrival. Since there are only one server, when a customer arrives, the time he needs to wait to his turn is the sum of remaining service time of all the customer in front of him, which is the work in the system. By taking exponential of both sides, we will get WQ to be equal to the average work as seen by an arrival. This is equal to V due to the Poisson arrivals. Then, by substituting this into the equation of average work in the system, we will get WQ. Besides, the fundamental identities LQ, W, and L can be obtained easily by the formula shown in the slide. Next, let's look at an example. The special thing in this example is the sketch sentence. Independently of all that has previously transpired, each new arrival is type I with probability alpha I, where the sum of alpha I from 1 to R is 1. Also, different type of customer has different service distribution Fi with mean mu I and variance sigma I squared. Then, we wish to find the average time of a type J customer spent in the system, Wj, and the average number of type J customer in the system, Lj. Since this is not classical MG1 model, so we need to find out the general distribution of the service time first. Since the service time depends on the types of the customer, we use a conditioning probability on the type of customer to compute the service distribution G. Also, we use conditioning probability on the type of customer, the expected value of S and S squared. Then let WQJ to be the average time that a type J customer spent in queue. Then by the WQ equation that we have derived before, we will get WQJ. Also, since WJ is equal to WQJ plus expected value of S, and Lj is equal to lambda alpha J times Wj, we can get Lj and Wj easily. Consider the system alternates between idle periods, there is no customer in the system, and busy periods, there is at least one customer in the system. And we let I and B to be the length of an idle and busy period, respectively. It's easy to see that I is exponential with lambda when the customer arrives with a Poisson distribution lambda, because I represent the time from when a customer leaves the system empty until the next arrival. Thus, the expected value of I is 1 over lambda. To determine the expected value of B, we use the long-run proportion of time the system is empty, which is P0. Then, from the fundamental cost equation, by supporting that a customer pays at the rate of 1 per unit time while in service, the average number of busy service is equal to lambda ES. On the other side, we know that the average number of busy servers is the total number of servers times the average number of the idle period, which is 1 minus P naught in MG1 model, since there are only one server. Thus, P naught is equal to 1 minus lambda ES. And therefore, we can get the expected value of B by equaling both P naught equation. Besides, we are interested to find the number of customer server in a busy period, C. Note that for every EC arrivals, only the first customer will find the system empty. Thus, A0 is equal to 1 over EC, where A0 is the proportion of customers that find nobody in the system when they arrive. Moreover, A0 is equal to P0 due to the Poisson arrivals. Thus, we can compute the expected numbers of customers served in a busy period as shown in the slide. Furthermore, we will consider the case of random size batch arrivals. That is, each arrival is a Poisson distribution with red lambda, but consists of a random number of customers. We let alpha j to be a probability that an arrival with j customer and n to be a random variable representing the size of an arrival. By the V equation we derived before, and the fact that lambda a equals to lambda times expected value of n, we will get the equation as shown in the slide. Let WB to be the customer waiting time due to those in his batch. In this case, a customer wait in queue is not only the work in the system when he arrives, but also need to consider his waiting time due to those in his batch. Thus, WQ is equal to V plus the expected value of WB. Compute the expected value of WB, we first determine the probability that the customer came from a batch of size J, which is J alpha J over expected value of N. Then, by conditioning on the number of the batch, we can get the expected value of WB by computation in the slide. Note that the second line of the equation is because for a batch of J customer, one of the customer needs to wait for n-1 of them to be served if he was I in line among his batch members, and we assume he is equally likely to be in any position among the batch. Finally, by substituting V and the expected value of WB into WQ, we obtain WQ as shown in the slide. Next is a system with periodic queues. Consider the situation where there are two types of customers which align according to independent Poisson process with respective rates lambda 1 and lambda 2, and have service distribution G1 and G2. We suppose that type 1 customers are given service priority, in that service will never begin on a type 2 customer if type 1 is waiting. However, if a type 2 is being served and a type 1 arrives, we assume that the service of the type 2 is continued until completion. Our task is to compute WQI, the average wait in queue of a type I customer. Note that the total work in the system at any time will be exactly the same no matter what priority rule was employed. Thus, it is just MG1 model with lambda to be the sum of lambda 1 and lambda 2, and the general distribution G can be obtained by conditioning on which priority class the arrival is from, as well as the service time. Again, using the V equation to obtain the equation below. However, note that S and WQ star are dependent on the priority model since different type of customers have different service time, thus the waiting time will be also different. Thus, we compute the average amount of type 1 and 2 work in the system separately. Let Vi to be the average amount of type I work, VQI to be an average type I work in queue, and VSI to be an average type I work in service. Then, we can obtain these three equations by the V, VQ, and VS equation we derived before. Now, consider a type 1 arrival. Then, his waiting time is the sum of the type 1 work in the system and type 2 work in service when he arrives. That is V1 plus VS2. And the results are shown in the slide. Besides, note that V is equal to WQ1 plus VQ2. Thus, by some calculation, we can get WQ2 and shown in the slide. Next, we'll look at an MG1 optimization example. Let rho to be equal to lambda ES, where S represents a service time random variable. Suppose that the server departs whenever a busy period ends and does not return until there are n customer waiting. At that time, the server returns and continues serving until the system is once empty again. If the system facility incurs cost at the rate of C per unit time per customer in the system, as well as a cost K each time the service returns, we're interested to find out a value N that minimizes the long run average cost per unit time incurred by the facility and the minimum cost. Before that, there are several notations that need to be introduced. Let N to be the average cost per unit time for the policy that returns a server wherever there are end customer waiting. Cn to be a cost incurred in the circle. Tn to be the time of a circle. Ti to be the time interval from the first time during the circle that there are I customer in the system until the first time afterward that there are only I minus 1. Ci to be the cost incurred during the interval of length Ti. Wi to be the sum of the initial service time plus the sum of the time spent in the system by all the customer until the moment when only left I minus 1 customer in the system. And WB to be the sum of the time spent in the system by all arrivals in an MG1 busy period. Then, by renewal reward process that we learned before, AN is equal to the expected value of cost incurred in the cycle divided by the expected value of the time of a cycle. Next, we know Tn is the busy time of the server during a cycle, which is the sum of Ti from 1 to n plus the idle time of the system until arrival of n customer. By taking expectation, we will get the first equation as shown in the slide. Then, since service time do not depend on the order in which customer are served, the time that it has to go from I customer in the system to I minus 1 has the distribution of the length of an n G1 busy period B. First, we will get the second equation, resulting the last equation by substitution. Then, for expectation value of the cost incurred in the system, as shown in the first equation, the first two terms is the total cost incurred during the busy part of the circle, and the last term is the cost incurred during the idle part. To attain Ci, consider the moment when the interval of length Ti begins. Thus, Ci can be treated as a cost incurred due to the I minus 1 customer in Q during the interval of length Ti plus the cost incurred during the interval Wi. And taking expectation of both sides, we'll get the result by the fact that Wi has the same distribution as Wb. Next, to compute the expectation of Wb, we use W equation and the renewal reward process to get two W equations, including the expectation of Wb. Here, n is the number of customers served in an MG1 busy period. So the expectation of n is 1 over 1 minus rho. Then we can compute expectation of Wb and Cn. And the results are shown in the slide. Finally, by substitution, we can get an equation of An, and we differentiate it with respect to n. Setting A prime n to be 0, we'll get the optimum value of n and the minimum average cost per unit time as shown in the slide. Last but not least, we will go to the system with server breakdown. Suppose that we're working, the server breaks down and at an exponential rate alpha. When the server breaks down, it immediately goes to repair facility. The repair time is random variable with distribution h. Also, suppose that the customer in service when a breakdown occurs has each service continue when the server returns from the point it was at when the breakdown occurred. Thus, the actual total time a customer receives service from a working service still has a distribution G. Next, let T to be amount of time from when a customer first enters service until it departs the system. S to be a system service time, N to be a number of times that the server breaks down while the customer is in service, and Ri to be the time of the server spends in the repair facility on each successive visits. Note that T is a customer service time including the waiting time for repayment and also a service time random variable of this MG1 Q. Thus, we can get WQ by what we derived before. To compute the expectation of T and T squared, note that T is actually the service time plus the sum of the time the server spends in the repair facility, which is the first equation on the side. Then, by conditioning on the server time s equal to x, the number of server breaks down while the customer is being served is a Poisson random variable with mean alpha s. Hence, we will get the second and third equation where R has the repair distribution h. And this implies the last two equations. By conditional expectation and conditional variance formula, we can get the expectation of T and T squared, as well as WQ as shown in the slide. In short, we've introduced the model MG1, where the service time becomes a general distribution but not Poisson distribution. Different cases such as BD and idle periods, random size batch arrivals, periodic queues, and server breakdown have been studied in order to help us understand more about the real-life cases. However, we can still study more deeply about the more general cases and model. For instance, for periodic queues, we can assume that there are n types of customer instead of 2 types of customer. In the queue with server breakdown, there are some interesting quantities that can be studied also, such as the proportion of time the server is working is being repaired and is idle. Study on GM1 will be more difficult from the fact that the number of customers in the system is not informative enough to serve as a stat space. Lastly, multi-server queues, MGK is also interested to be studied, and we are interested to study the roll-run proportion of time that I service is working, PI, in the multi-server queues by using the balance equation. And that's all for me. Thank you.